to make sure as well that our water treatment facilities can actually filter these things out. And the last of the technologies then, which we've been looking at, is new materials. And again, its advances in data science, in growing computational power, and simulation techniques, which are allowing material scientists to create materials with almost entirely new properties, properties which haven't existed in nature before. So, for example, metals which will shrink when they're heated instead of expanding when they're heated, or solids like this aerogel that have a density similar to the density of air used in the aircraft industry. So the point is now that the material scientists, instead of as in the past when a user would look for desired qualities in a large sample of materials, now you can work the other way round. So the era of trial and error in materials development is coming to an end because of the digital revolution. Now the engineers start with the qualities that you're looking for in the material and then build the material from the microstructure up. So even within the same block of metal, for example, the different qualities of that metal can be made to vary in a controlled way across the length of the material. And this means that engineers will not only design the products of the future, they'll also co-design or simultaneously design the materials from which those products are made. And this will have major competitive implications. You think if you're a car company, you've designed a particularly efficient engine. Your competitive standing is much stronger if you also own the materials from which the engine is constructed. But again, there's a variety of policy issues. Just one of them I'll hark on. The chapter in the book on new materials was written by the head of the materials science department at Georgia Tech University, and I was really intrigued to learn about the possible threat of new cybersecurity risks, as we'd mentioned security. And the issue here is that if you have a simulation or digitally based pipeline of new materials, this could be vulnerable to hacking. So those who are ill-intentioned could deliberately introduce a digital flaw into the material so that, say, a critically important material will break after a certain number of flexions and so on. So I'll talk now just briefly. I'll see how much time we've got. Okay, so I've already been on this for just nearly half an hour. I will maybe talk for another 10 minutes and then open to Q&A. So talk about some of the cross-cutting issues, what governments need to be alert to. It's critically important that governments institute sound science and R&D policies. Many of the technologies, as is evident that we've referred to, are deeply linked to advances in science. And the policy issues here are many, from the size of public R&D budgets to how these budgets are allocated and evaluated. And public investment in R&D has been particularly critical. We're only at the position we are now with artificial intelligence, where it's estimated that the big five in the US will this year invest something like $50 billion in R&D, or much of it related to artificial intelligence. We're only in this position because of public investment in moving artificial intelligence forward since the end of the Second World War. Similarly, this technology here, the gene editing technology, CRISPR-Cas9, which is ushering in enormous changes in the world of biotechnology, this can be traced to an accidental discovery during public research on the E. coli bacteria in the late 1980s. So public investment in R&D is essential, and yet, unfortunately, many governments, their commitment to long-term investments in basic research and in R&D are declining. It's great you can generate huge wealth if you're a technology developer, but for most countries and most companies, they will primarily be technology users. So that means that governments have to be concerned with getting the maximum number of firms, entities, which are able to use, which understand how to use the technology. So technology diffusion is a key issue. And we see there are many problems with technology diffusion. So take, for example, this technology, this is showing us cloud computing. So cloud computing is a technology which should level the playing field between small and large firms in terms of access to computation. And yet you see, there's huge differences across countries in the extent to which cloud computing is used by business. But when you look at the balloons at the top and going down, the balloons represent the share of companies in that country which are large, so companies which have over 250 employees. And so if you look at Finland on the far left of the graphic, so that shows that about 70% of large Finnish firms use cloud, but only about 50% of all enterprises use cloud, an even smaller percentage of the smaller firms. And so you ask, why is this? Should be a technology which both sets of firms could use equally. We see this is a problem in many other areas. So, for example, precision agriculture, it's the large farms which use data-intensive precision agriculture more than the small farms. These are the second-generation robots. This is an example called Baxter. So unlike the first generation of industrial robots largely used in the automotive industry, these are small, they're not particularly expensive, they're flexible, you don't need to be a computer scientist to operate them. Some of them will just observe the movements of the human worker and then mimic those movements. They're suitable to small batch size production, which is particularly apt for SMEs, and yet in Europe, 36% of companies which are small use these industrial robots, only 36, but 74% of large firms with 1,000 plus employees use them. In fact, I mentioned the growing criticality of supercomputing, and there's been estimates in the United States that about 8% of US firms with fewer than 100 employees, that's 8% of US firms with fewer than 100 workers use supercomputers, but potentially about half of manufacturing SMEs could make use of supercomputing for prototyping, testing and design. So there's a big unbridged gap there in terms of technological potential. And we see this is a quote from Angela Merkel from the World Economic Forum of 2015, where she said, "We have to execute quickly, otherwise those who are already leading in digital will snatch the industrial production from us." And we tend to think of Germany as being the cradle of Industry 4.0, one of the technological juggernauts, and yet it's very surprising to see the actual data show that from a survey in 2015, quite a large survey, 4,500 firms, only 4% of German businesses had implemented digitalized and network production or had plans to begin doing so. So again, a huge diffusion challenge. And we can look at diffusion from another angle, and that's that those companies which are born with the intention of using these technologies, they need to operate in an environment which is propitious, which is conducive to growth. And we see big differences across countries in the ability in the ease with which companies can grow, linked to a whole series of framework conditions around bankruptcy regimes, around regulatory and administrative burdens, the operation of the venture capital system, etc. So this is just showing us the amount of external capital that each firm can access for each 10% increase in the stock of patents. And you see there's almost a threefold difference between the US and Italy. And we also need a healthy rate of business births, because new firms, one, they're particularly important in introducing new technologies, especially in ICT and biotech. But these new firms, perhaps more importantly, they're not constrained by legacy systems. They can introduce more easily the new business models which are required to leverage and extract value from the technologies. And there's a really lovely historical example of that, which was described by the Stanford economist Paul David in a 1990 paper looking at the impact of the electric dynamo, which was literally the engine of the second industrial revolution, the impact that it had. So this is how factories were organized in the 1860s. So factories had many floors built around a central steam engine with drive belts from an overhead transmission apparatus, and with all the machines running at the same speed because they all ran off the same set of drive belts. And then in about the 1890s, we got the introduction of the electric dynamo, the commercialization of electricity. And what did business people, what did entrepreneurs first do when the electric dynamo became available? They took out the steam engines and they replaced them with electric dynamos, but still with the same transmission systems, and there was no change in productivity. In fact, there was a major slowdown in industrial and aggregate productivity in both the US and the UK during the period of 1890 to 1913, the US and the UK were the two largest industrial powers of the day. So they experienced a decline in productivity when this new technology became available. And so this speaks to, there's an echo with our current circumstances, where we have all these new digital technologies, but sluggish productivity growth. And then from the mid-1890s, eventually, businesses figured out that factories could be completely redesigned on a single floor. And so production was arranged so that each machine was attached. Each machine was attached to its own electric dynamo, the so-called unit drive. And then, from about 1920s, 4 decades after the commercialization of electricity, the dynamos, US productivity growth leapt. It was about 5% per annum. And particularly in those sectors where there was a high rate of business births, that's to say new entrepreneurs who figured out they could use new business models, rearrange, reorganize production, and that was where the productivity growth was fastest. I'll close now with just a couple of observations about skills and the labour market. And I mean, everybody's interested in this. What's the future of automation? And we are seeing that there will be big changes. There are major changes occurring in the labour market today. So we're seeing, for example, complex aspects of the work of software engineers can be performed by algorithms. Computer-based managers are being trialed, and my favorite example is the one at the bottom here, where we see that some recent softwares interpret human emotion better than humans by observing micro-expressions. And this really foreshadows a sort of new era of much more subtle machine-human interaction, and I think there's interesting things to say there. Something's missing on the diagram. Okay, something's missing there, but I was just going to put up a graphic which showed that according to the OECD survey of adult skills, recently PIAC, the Programme for International Assessment of Adult Competencies, about 2/3 of the adult population lacks the skills for the digital age. So there's issues of the overall supply of the required skills, but also issues of insufficient interdisciplinarity, the question which I raised earlier. And this then is my final slide. And one is that policy needs long-term thinking in this area, not just thinking which is governed by the sort of the imperatives of the next election cycle. So Germany, for instance, has created an Industry 4.0 steering group that will operate over the long term. For a while, Sweden has had a ministry for the future. But working in many OECD countries, you never see a labour ministry, for example, which has a plan B in the case that